How's it going, Earth Science? Welcome to Earth Science from Home. I am Mr. P, if you don't know. I don't know if you remember me yet. Um, but we're going to do just a little bit of notes today, not too much, and we are going to talk about some new stuff, which is kind of nice, and then you'll have a whole bunch of different other things to do for this week. But the notes for this week should be nice and short. And the things we're going to talk about, alright, here. So here's our goals for today in terms of the notes. What we're going to do is we're going to first define the different layers of the Earth. As Shrek said, the Earth is like an onion, has multiple layers to it. We're going to describe what the theory of continental drift is, and most importantly, what evidence do we have that proves the theory of continental drift. Okay? And the only thing I ask of you is that you have your Earth Science reference tables out to page 10. This is going to be super important, and you're going to have a set of questions specifically on page 10. The questions that you're going to be answering this week, it might seem like completely out of the blue, because a lot of the questions are completely out of the blue, but every single answer is on page 10, so that's all you have to worry about. It's all actually the pre-class activity they do now that I would have used for you if we were in school. And so let's talk about some of these things. So, the layers of the Earth. What we call it the dynamic crust, because the crust of the Earth actually changes. It moves, it alters itself. There's new crust that is being made, there's old crust that is being destroyed. And so we just describe the Earth in 4 layers. The crust, the mantle, and then the inner and the outer core. So, obviously, we're going to go from outside to in. So the crust, well, that's where we are right now. The crust is the outermost layer. It can either be an oceanic crust or a continental crust. So continental crust would be the crust that we are living on. Oceanic crust, that's where the oceans are. So the outermost layer is mostly granite if it's continental, or basaltic if it's oceanic, and the continental crust is a lot thicker than the oceanic crust. So we either have granite making up our Earth, the layers of our Earth that we are standing on, or basalt, which is the thinner oceanic layers. Now I'm going a little fast. Feel free to pause and write down the notes. I know that we don't have any guided notes, so I'm going to keep it short for today. That's why. So, lithosphere. The lithosphere is all of the crust in the upper mantle, and we call these plates. Now, they are not plates that you eat off of, but they are pieces of our crust. There are pieces of our Earth that are actually free to move around. And we'll talk about these a whole bunch, but keep that idea in your head, the idea that our crust is broken up into plates, into pieces. The moho is a very dense layer, and this is super important when we talk about earthquakes. Earthquakes, seismic waves, when we talk about these, you'll see this term moho, and most importantly that it's dense, and the reason why we care about it like that is because certain seismic waves, certain earthquake waves cannot pass through. Okay. Mantle. Mantle is the biggest piece of the Earth. And the biggest part of the mantle that we care about is the asthenosphere. I always mess up saying that. This is actually what allows the plates to move. So the asthenosphere is largely iron, and that iron can sort of almost just get to the point of melting and get to the point where it could start moving around. And so because this piece of the Earth can sort of move around, we can allow those plates on top of it to kind of move back and forth. It's almost as if the plates on top of the Earth are just a little surfboard, and the asthenosphere is just a little bit of putty that can move around and allow our continents to kind of move. So now we have our cores. The outer cores is liquid, at least from everything that we've seen, and the inner core is solid. And so these two, you mostly only need to know that the outer core is liquid and the inner core is solid. I wouldn't even worry about writing anything in this piece down, other than the inner core is inferred to be solid because of its behavior in seismic waves, and it is believed to be composed of iron and nickel. You could stop your notes right there. Okay? Okay. So that's the layers of the Earth. Look, check one of our goals done. Now we're going to be talking about continental drift. So, we had this scientist, German scientist Alfred Wegener, believed that, well, he was actually a meteorologist, and he believed that the Earth's continents had actually once existed into one giant landmass. They were all pieced together into what he called Pangaea. And that these continents, while they were once together in Pangaea, are now just separate continents because they have moved away. And he was essentially laughed at in his time period because, well, it was a crazy theory. It was the idea that the continents were somehow together. And he essentially saw it as, well, the puzzle pieces fit together. You could see that the eastern coast, say South America, fits in with the western coast of Africa. It all looks like it pieces together really well, but he did find other pieces of evidence that were even more important. And here's the other two pieces. So first, mountain ranges and rock types between multiple different continents actually do match. If you look at continental mountain ranges, say for like even the eastern United States and western Europe, the mountain ranges actually do connect and link up. Same thing with the southern parts of Africa, specifically, and Australia, and the southern parts of India. All these mountain ranges also match up and have the same rock structure. So with those two ideas that, wow, these mountain ranges do connect like a line and they are made of the same rock, maybe they actually are the same mountain ranges that were split up. And lastly, this is what we talked about in terms of our pre-class activity, the idea that there were fossils of prehistoric creatures found in completely different continents that had no evidence of being able to swim. The only way that could possibly happen is if the continents were once together. If there was a time where the fossils were able to actually exist in one landmass, and then that landmass separated, rather than the animals building a boat and going to the other side. And so the last thing I want to talk about is mid-Atlantic ridges or mid-ocean ridges, but that's basically it for the notes. Here's a little picture of Pangaea, which is kind of nice, so you could see this. So that's the South America eastern coast and the western coast of Africa kind of matches in perfectly. Even North America looks like it kind of fits right in there. And so this is just like a bunch of puzzle pieces. And here is our fossils as well. So these fossils connected right along not only mountain ranges, but also connected between all of these different continents. And so these are very common fossils that we use to prove the theory of continental drift. All right. So we're going to talk about this next week, but this is a mid-ocean ridge, and I have a little demo of it right here. And so what we're going to have, or what we're going to start to look at, is as we have this lithosphere, which the top part of the lithosphere is called the asthenosphere. And so as we move outwards, we're going to have this crust moving outwards and new crust being made here. And this is kind of where we're going into with our unit. How does this crustal movement affect the Earth, and how does it shape the Earth in ways that you've maybe already seen, but maybe just not have attributed it to the theory of continental drift? Alrighty. Thanks. See you guys later.